Hey everyone, my name is Ajay and welcome to SD-WAN series part 4. Agenda for part 4 is going to be application quality of service, packet duplication, packet fragmentation, tunnel overhead and MTU. And then we are going to talk about some of the SD-WAN features. So let's get started. It is quality of service. If you are dealing with the network services, then you are all aware about how the marking and the classification of traffic works, and the quality of service which is assured, and the SLA and everything is committed by your service provider. So for example, here on my screen you can see a machine. This can be a SD-WAN equipment, and then you are connected to a service provider which is AT&T. If it is a normal router, let's say, which is from Cisco, this machine is connected here on the LAN and you are connected to the WAN. Then you have another remote site, and somehow you form some sort of the GRE tunnel which is over this MPLS. So anytime a packet which hits the LAN side of the router, it is marked with some of sort of the DSCP values. So let's assume we are talking about the VoIP traffic, and that traffic will be marked as EF. So when this packet hits the router, you need to do some sort of marking, or you need to honor whatever the coming from the LAN side. When this traffic passes over the router, if you don't have any sort of overlay, it will be passed over the MPLS, and your service provider is going to commit you some sort of SLA and the commitment in terms of how they are going to handle the traffic prioritization. So in this case, let's assume this is provided by AT&T. There are 5 different values, so cost1 to cost5. These are the traffic which is going to get priority within the AT&T cloud. So this is the committed bandwidth. So 5% of the total bandwidth which is provided by AT&T is going to have cost1. Similarly, you're going to have the 20% in cost2 V and 20% in cost2, like that. So let's assume we are talking about the VoIP traffic, which is going to be the real time. So whenever the real time traffic, it hits the MPLS cloud, it is going to reserve 5% of the total bandwidth, which is going to get the prioritization within the cloud. Now let's assume the same traffic, it comes and hits the router, and this time you have some sort of the GRE overlay configured. So what will happen? This actual marking on the packet, which is going to be the DSCP value, will be hidden by the new encapsulation you might have. Once this value is hidden, it is going to be the regular traffic. So what I mean, you're not going to get any sort of the prioritization with this traffic travels from AT&T cloud and reaches to another site. You're not going to see any sort of the prioritization. Now, when we are talking about SD-WAN, so in a SD-WAN, it is going to be the feature which is going to look at the DSCP value of the actual packet, the original packet, and going to copy the same DSCP value to the new encapsulated packet. So this time it is going to have the same value, which is hidden here, but you copied this value to the external header. Now, when this traffic travels over the MPLS, it is going to carry the actual marking. So this DSCP and the classification for the KOS, it is going to work for you. Let's talk about FEC, which is forward error correction. This is a concept which SD-WAN has taken from the RAID 4 setup. So RAID 4 basically is the storage array which we use. So let's assume whenever you're going to write some of the data on the hard disk, it is going to be in different hardware, which is going to be the different hard disk configured. So let's assume this is the first block, This is the second block, third and fourth block. Whenever you write some sort of the data, so let's say some data is coming here. So it is going to do a write operation for all the disk. Some data will be here on the A0, A1, A2, and A3. Based on the digital XOR operations, it is going to generate the parity. And the parity bit you need to write on a extra hardware which you need for that. So here it is going to be the extra hard disk where you're going to write the parity bit. So in case of failure, which is very, very common nowadays, maybe you're running a big data center and every day you see some hard disks are getting failed. The moment the hard disks are getting failed, we are worried about what will happen to our data. So this is a technique you can reconstruct your data which is on the failed device. So let's assume this hard disk fails. You still have A1, A2, A3 and the parity bit. You are again going to do the XOR operation and you can generate or reconstruct the data which you lost here on due to this hardware failure. So let's see how it works on the SD-WAN side. I'm sending a flow which is 4 packet 1, 2, 3 and 4. I'm going to add an extra bit which is going to be the parity bit. So parity bit is nothing, it is just going to have the check bit which might be even and odd parity. So when I'm sending this flow over the SD-WAN tunnel, I might have some lossy link in between. Maybe this is all internet infrastructure. And I lost this packet, which is the fourth packet. So I still got packet 1, 2, 3 and the parity bit. So based on the parity bit, I can reconstruct this lost packet. In a regular scenario, if it is not a SD-WAN, what will happen? This lost packet has to will be retransferred from this device to another device, which is going to consume a lot of round trip time. So we need to understand here, since we are doing a reconstruction of lost packet, which is based on the parity bit, but not everything can be recovered. As per Cisco, only one packet out of 4 can be reconstructed. So we need to keep in mind how lossy is the link, how many packet can be recovered to get the desired quality of your data transactions. Now there's another feature which is called the packet duplication. In the packet duplication, if your traffic is very, very mission critical and you don't want to lose any of the packet, so trick which you can do, there's a tunnel which is, let's assume this is formed based on the MPLS and the second tunnel is on internet, and you know it, these both links can have some sort of the packet drop. So what I'm going to do, I'm going to send a same stream which I'm sending here to the second link. So my first packet, second packet, third packet, and fourth packet, it travels over the first tunnel, and the same flow packet 1, 2, 3, and 4 also goes over the second link. So in case I lose this packet over the MPLS, I might lose packet 4 over the internet. I got a lot of duplicate here. So from first link, I got packet 2, 3, and 4. Over the second link, I got packet 1, 2, and 3. This SD-WAN equipment, it is going to discard all the duplicates and going to reconstruct the same sequence what we were sending from initially from the sender. Let's look at the animation. We lost the packet 1, then we lost the packet 4 on the second link, and when it comes to the reconstruction, all the duplicate will be removed. Now let's talk about the fragmentation and the network layer. A typical network provided over the Ethernet will have 1500 byte MTU configured on all the interfaces. But since we are talking about the internet, you might have different media involved in between, which you cannot guarantee. So your MTU value will differ from one physical media to another physical media. Fragmentation is not a it's not a good sign for quality and performance. So we should avoid the fragmentation. We are going to look at how SD-WAN takes care of the fragmentation and gives us a better performance. So on the token ring, your MTU value is going to be this. And for a 4 Mbps token ring, it is going to be 4464. Ethernet, as I said, is going to be 1500. If you have point-to-point over the Ethernet, it is going to be 1480. So there are different medias and there are different MTUs configured on those interfaces. To avoid fragmentation, we need to find out what is the maximum packet size that can be handled by the operating system on the both end. And what is the maximum allowed datagram size that can travel through the physical connections between the host. The maximum packet size that can be transmitted without fragmentation between two remote hosts is called the path MTU. And in SD-WAN, we are going to discover this path MTU automatically. So these are the two branches, and I have SD-WAN equipment installed both the end. So SD-WAN proactively discovered the path MTU across overlay fabric and participate in host PMTU process by notifying them of the available MTU. So this is a MTU discovery. Larger MTU in case received, you need a fragmentation. So it is going to notify you back, reduce the MTU value. And you're going to reduce until you achieve no fragmentation. That is the goal, going to be the value between these two. Now let's talk about the tunnel overhead and MTU here. We all know whenever we do some sort of the encapsulation by using the IPsec tunnels, all those things, it is going to add some extra bytes in terms of the overhead. So in the SD-WAN setup, the tunnels those are formed, they're going to use the ESP as a protocol for the encryption that is going to add the overhead of between 66 to 81 bytes. And your path MTU discovery will measure MTU to minimum somewhere between 1300 to 1400 bytes. So this is my actual data. You have the IP headers, you have TCP headers, and you are going to have the data. When we encapsulate this packet over the IPsec, you are going to insert a ESP header, and there are going to be the new IP address. So for example, we all know Ethernet is going to be the 1500. So I just mentioned the 1500 all over the place. So in the 1500, it is going to be 20 bytes for the IP, 20 bytes for the TCP, and rest is going to be your data. So technically it is 1460 bytes which you can send, which is called the MSS value. And the MTU value is going to be, if you add everything, which comes to 1500. So this machine, which is trying to send data over the IPsec tunnel, it signals for 1460 MSS value. And whenever this packet hits to SD-WAN equipment, it is going to adjust based on the overhead it is going to add. So let's say this adjusted 1300, which is being communicated to the remote host. And the similar thing happens, the remote host is going to signal for 1460 based on the Ethernet, and this SD-WAN is going to adjust for 1300. So when they both receive the adjusted MSS value, they agreeing for 1300 MSS value, which can be transferred over this IPsec tunnel. Now let's talk about another feature which is called software-defined application visibility and control. In this feature, SD-WAN uses the DPI. So it's a DPI engine where you have some sort of the signature already installed, and whenever your traffic passes that through the SD-WAN equipment, your DPI engine can detect what kind of application signatures are there, and it can identify what type of application you're transferring. Let's talk about a old router. Maybe if you ever configure that Cisco router, you need to enable the N-bar protocol discovery. And once you enable it on the interfaces, it can tell you what kind of traffic it is being passed. So let's assume from the LAN side, there are three flows coming. My first flow in blue, my second flow in green, and the third flow in red. Based on the DPI, you can route your traffic based on application detection. So when we talk about the old infrastructure, which is based on the Cisco router and switches, we call it IP routing. And here we are talking about a application routing. So that's the difference. Here you're routing the application. You can tell if my app one, this is an application which is coming from app one, and if it is being detected by the DPI, you send it over the broadband. My app 2 application data, it has to go over the MPLS, and my app 3 data, it has to go through the 4G. And on the Cisco environment, if I can recall it, you need to update these NBAR signatures whenever you get the update to recognize the new and latest applications. In the SD-WAN infrastructure, you are going to have this connectivity to Cisco to download all the new signatures. So it is something automated. Thank you, everyone. I will see you in the next video.